In chapter 6, we're studying linear programming problems. Now, a linear programming problem is when we are trying to optimize an objective function based on certain constraints to the problem. When we optimize, what we mean is we're trying to find the maximum value of this function or the minimum value of this function. Now, there are two different methods that we're going to see in chapter 6. The first one is the method of corners, and the second is the simplex method for solving these linear programming problems. So we're going to look at the method of corners first. Before we get to this method in 6.1, we're just reviewing how to graph a linear inequality and graph a system of linear inequalities. That's key to this method of corners. So let's take a look at that first. So as a review, to graph a linear inequality, we're going to first replace the inequality sign with an equal sign and graph that linear equation, just like what we've done in the previous algebra chapter. Okay, then we'll use a dashed line for that graph if the inequality is strict, if it's strictly less than or strictly greater than. And we'll use a solid line if the inequality includes the line itself. If you are using the less than or equal to sign or the greater than or equal to sign, that's when you'll use the solid line. Okay, once you graph your line, then you'll choose a test point on either side of the line. If the origin is available, that point 0, 0, that's the easiest one to use. And you'll plug that into the inequality. If you get a true statement, then you will shade on the side that the test point lies on. If you get a false statement, then you'll shade on the side opposite of where the test point is. Okay, so let's take a look at this example to see how these steps work exactly. All right, so we're going to graph this linear inequality 2x plus 3y less than 6. So we're going to graph this just as we would the linear equation 2x plus 3y equals 6. And there are different ways you can graph this. You can write this in slope-intercept form, right? Graph the y-intercept and then use the slope to find a second point. What I like to do in this case, especially when it's written in this standard form, is to find the x-intercept and y-intercept. Remember, we can find the x-intercept by letting y equal 0. Okay, so when we let y equal 0, that's basically setting the y term equal to 0, right? So when y is equal to 0, just think of that 3y term canceling out, and we're left with 2x equals 6. And then we'll divide both sides by 2 to get x equal 3. And that is the x-intercept. And you can write that as a point 3 comma 0. There's my point 3 comma 0. And then I can do the same thing for the y-intercept, except I'm letting x equal 0. And when I let x equal 0, we're essentially setting that x term, 2x, equal to 0, right? So we can just mark through that or cover it up and solve for y. This 3y equals 6. Divide both sides by 3 and we get 2, and that is our y-intercept 0 comma 2. And now that we found the x and y-intercept, 2 points to find a line, so we can draw a line through our 2 intercepts, and we have our line. Okay, but now look at the inequality sign. Right? Is it strict or does it include the line itself? Right? Is strictly less than. So we don't want to have a solid line. We want to have a dashed line. So I'll use my eraser here and draw this again. I thought I could erase just pieces of it. All right, I'll just draw this again using a dashed line going through those 2 points. All right, so the dashed line just means that we're not including the line. okay, because it's strictly less than. All right, so which half plane, right? This line is dividing the region into two different parts, right? So are the solutions included above the line or below the line? This is where the test point comes in, right? So we can choose any point. It does not matter which point that you choose, but I'm saying that if the origin is available, right? The only reason that the origin would not be available is if the line went through the origin already, right? If the point 0, 0 lies on the line, then you couldn't use it. Otherwise, you can use it, right? Such as in this point, the origin lies right below this line. So I'll use this as my test point. Zero, zero. And then I'm going to substitute this into the linear inequality. All right, so I'm going to plug 0 into x, 0 into y. See, that's why it's so easy to use the linear inequality, because there's really not any math that you have to do, right? Because if x is 0, y is 0, both of those go to 0. So we've got 0 less than 6. All right, so now is this a true statement or a false statement? 0 is less than 6. That is true. So since it's true, we are going to shade on the side, on the half plane that the test point lies in. Okay, so every point in this shaded region, every point below this dashed line is a solution to our linear inequality. All right, so now we'll take a look at some additional examples of just graphing linear inequalities. Then we'll jump to a system of linear inequalities to see how that works, which is just the same as graphing individuals. All right, let's take a look at this one. Graph negative 3x plus 6y greater than or equal to 12. And so we'll do the same thing as far as finding the x-intercept and the y-intercept for this. For the x-intercept, we are letting the y term go to 0. So we've got negative 3x greater than or equal to 12, right? Divide both sides by negative 3. So 12 divided by negative 3 is a negative 4. So our x-intercept is negative 4, 0. All right, so not much work you have to show with this approach, finding the x and y-intercept, right? You just cover up the y term, solve for the x, and vice versa for the y-intercept. We'll cover up the x term now, right? We let the x value go to 0. So we've got 6y greater than or equal to 12, divide both sides by 6. And we've got the y-intercept of 2. That's 0, 2. So now we can graph this. Negative 4, 0, and 0, 2. And we'll draw a line through these 2 points. Now, what kind of inequality do I have here? I have a greater than or equal to inequality sign. So we're going to use a solid line since it's greater than or equal to, meaning that we are including that line that I've just drawn. So, okay, so now am I going to be shading above or below that line? Again, we can choose a test point. If 0, 0 is available, we choose that one, which it is. So we'll use this point 0, 0, plug it into the linear inequality. We like 0, 0 because there's really no work you have to show here, because I know the left-hand side is just going to be 0. And then we look at the statement, determine if it's true or false. 0 is not greater than or equal to 12. So this is a false statement. So we're going to shade on the half on the half plane that does not contain the origin 0, 0. All right, so we're shading above this line here. So every point in this shaded region will be a solution to the linear inequality. Okay, And I have one more example with just individual linear inequalities before we jump to the system of linear inequalities. This one is when we're graphing x less than or equal to 2. This one may look a little funny because there's no y term in there, but we can still graph this. Since there is no y term, there's not going to be a y-intercept, so it's not going to cross the y-axis at all. If you recall from our algebra chapter, the graph of the equation x equal 2 is a vertical line, right? It has an undefined slope. It has a vertical line. And so we know that this line will be straight up and down. It will pass through the x-axis at x equal 2, and every point on this line will have an x value of 2. All right, but we can still choose a test point, 0, 0, since it's available, and determine whether that's going to give us a true or false statement, and then do our shading. All right, so here is our origin 0, 0. So when x equals 0, is it's going to be a true or false statement, right? So we're going to plug the point 0, 0 into x less than or equal to 2. So that's 0 less than or equal to 2. Now, is this a true or false statement? 0 is less than or equal to 2. So we will shade on the side of that origin, that point 0, 0. So every ordered pair in the shaded region will be a solution to the linear inequality x less than or equal to 2. All right, so what about a system of linear inequalities, right? So we just have two or more linear inequalities put together, and we're trying to find all the solutions that satisfy this system. The procedure is no different. We're going to graph each of these linear inequalities on the same plane, and then we'll do our shadings separately, and then we'll see where those shadings overlap. Okay, so we'll start with a 3x minus 2y greater than negative 13 first. I'll go ahead and replace that with the equality. Okay, so the x-intercept, we let y equal 0, right? So we cover up the y, and we're left with a 3x equal 13. We divide both sides by 3, we get 13 thirds, right? Notice that all we're doing is we're dividing the constant on the right-hand side by the coefficient of the variable of the intercept that we're finding. So 13 divided by 3, 13 thirds is 0. And 13 thirds, you may want to write that as a decimal just to give you a better idea of what that is. 13 divided by 3 is what, 4 1/3. All right, so this point will be somewhere between 4 and 5, closer to 4 than it is 5. And I'll go ahead and label this just to help me keep track of what that point is. And then find the y-intercept. All right, we find the y-intercept by letting x equal 0, so we're left with negative 2y equal 13. And we can solve for y by dividing 13 by negative 2. Okay, so that is 0 comma negative 13 over 2. Negative 13 over 2 is negative 6.5. So that's between 6 and 7. Okay, so now we can draw a straight line through these 2 points. Okay, and now this is going to be a dashed line though, because it's strictly greater than. So let me go back and fix that. We want to have a dashed line. As it does not contain equality. And I'll make that as straight as I can. Okay. All right, and I also want to shade at this point before I move on to the next inequality. Okay, so am I going to shade above or below the line? I can pick my test point 0, 0, my origin, plug that into the inequality. Okay, can we do this just by looking at it? Sure we can, because I know when I'm using the origin, all this on the left-hand side is just 0. Is 0 greater than negative 13? Yes, it is. 0 is greater than negative 13. So we will shade on the side of the origin. So we'll shade this region here. Okay, so now we're ready to graph the second inequality, and we'll do this using a different color. I recommend using different colors. Very helpful when you're doing this with the systems of inequalities. So the negative x plus 2y greater than 5, we'll find the x-intercept by letting y equal 0, and we're left with negative x equal 5, or x equal negative 5. All right, so we have negative 5 comma 0. And then the y-intercept is found by letting x go to 0. And so we've got 2y equal 5, divide both sides by 2. That's 5 divided by 2, or 5 halves, which is 2.5. I'll graph the 2.5 between 2 and 3. And again, we have the strictly greater than, so I will use the dashed lines here. Okay, and I want to make sure that we see that these two lines will intersect, further up here, but they will intersect, they will cross each other. All right, and which side do we shade? All right, so again, we'll use the origin, the point 0, 0, and so that means that the left-hand side will become 0. Is 0 greater than 5? No, it's not. That's a false statement. So we will shade on the opposite side from the origin. All right, so now we have graphed both linear inequalities on the same plane, and the solution will be the overlap, wherever you see the red and the blue. All right, so that is, let me do this in black to highlight. All right, that's going to be everywhere in this region here. Okay, now this will be unbounded. All right, this will be unbounded because it includes everything moving up. All right, there's no bound to it. It keeps going. But everywhere, every point in that shaded region in the black, the red and the blue overlap, will satisfy both linear inequalities, so it satisfies our system of linear inequalities. Okay, I've got another example that we can look at. Okay, this one, graph 4x minus 3y less than or equal to 12. And also graph 5x plus 2y less than or equal to 10. And then we got two more linear inequalities, x greater than or equal to 0, y greater than or equal to 0. Now, these third and fourth inequalities, x greater than or equal to 0, y greater than or equal to 0, this just tells us that we're going to stay in the first quadrant of our graph. Okay, we're saying that x and y both have to be positive or 0, non-negative. Okay, and we'll see this in our application problems, to where we have this restriction that x and y cannot be negative. Since most of the time in our business applications, we're looking at the quantity, we're looking at dollars, to where we can only work with positive values. Okay, so we'll start with 4x minus 3y less than or equal to 12. There we go, 4x minus 3y equal 12. Okay, let's find the x-intercept first by setting the y equal to 0. So 12 divided by the coefficient of x, 12 divided by 4 is 3. So we have the point 3 comma 0. And then we'll do the same thing for the y-intercept. We let x go to 0, and we're left with negative 3y equal to 12. Divide 12 by the negative 3y, the coefficient of y, which is negative 4. So that's the point 0, negative 4. And since we have less than or equal to, we're going to use this solid line here. Okay. And which way we're going to shade? Right, we can use the origin. Right, so we let the x and y go to 0. So we've got 0 less than or equal to 12. That is true. So we're going to shade on the same side as the origin. Okay, then we'll do the same thing. Let's do this in red. 5x plus 2y less than or equal to 10. Letting the y go to 0, we've got 5x equal to 10, which gives us x equal 2. So we have the point 2 comma 0. And for the y-intercept, we let x equal 0, and we're left with 2y equal 10. Divide 10 by 2, we get 5. So we have our y-intercept 0 comma 5. And again, we are including equality, so we will use this solid line. Let me get my straight line here. That may look a little better. There we go. All right, which way do we shade? We let x and y be 0. Is 0 less than or equal to 10? Yes, it is. So we're going to shade on the side that contains the origin. All right, then of course we said that x must be greater than or equal to 0, y must be greater than or equal to 0. So we are working only in the first quadrant. So we're going to include the shading where you see the blue and the red overlap in the first quadrant. That would be this triangle right here. And so this would be our shaded region, our solution of the system of linear inequalities. When we get to the method of corners in our next video, we're going to call this triangle, right, this shaded region, the feasibility sets, right? These are all the solutions that could be the point that would optimize our objective function, right? And we're working with primarily the profit function, right? We want to maximize profit, right? So we would get a feasible profit by using any of these points inside this triangular region. But there's only going to be one. There could be more than one point, but typically one point that would maximize the profit, and we'll see how that works in our next video with method of corners.